All right, so most of you here, I hope, are doing some sort of MR research or at least clinical MR scanning. If done with care, MR is completely safe. It doesn't involve ionizing radiation. Our contrast agents don't involve any sort of iodine-based contrast agent that can cause kidney problems. The gadolinium agents that we use are much, much safer than that. The reason that we like MR is because we can do a multitude of different image contrasts, either structural or functional, in one examination. So why do we care about MR safety? So these are just a few different examples. So some of these slides you may have seen before. Richard sent them to me. They were used last year. So you can see people with cardiac pacemakers have died. People with certain types of implants have either been injured or had, like, for example, Parkinson's neurostimulators have been turned off by MR machines. This bottom example here, two 80-pound pieces of steel actually flew across the room and struck someone and actually made them fly 15 feet across the room, causing some serious injury. So this is just to give you a idea of some of the different types of injuries that can occur with MR. And I think the most famous example is the Michael Colombini incident. So in this particular case, the techs, basically the oxygen from the wall had run out or was not working properly, so the techs went into this little ante-room to try to get it turned back on. In the meantime, the respiratory therapist or the anesthesiologist was in the MR room calling for oxygen, and a diligent nurse comes running in with a giant metal oxygen tank, flew out of their hands, crushed the kid's skull. Okay? And as MR becomes more and more popular, we have to be more and more diligent about our safety with regards to the MR suite. So the learning objectives of this particular section. So we're going to review some of the key components of the actual MR suite, both hardware and actual infrastructure. And we'll talk about the safety issues associated with these particular parts of that. And then we'll just do some basic general speak review. So at the MR Center, yes, obviously this is the floor plan from the MR Center, and you can see Brad's name right there penciled in because that was one of his first desks. Yeah, exactly. And Kathy Wardell used to be where Pamela sits now. Anyway, so we've set up the MR safety structure with 3 different levels for operators. So level 0 allows you to have magnetic swipe access to get into this area here. Level 1 allows you to actually go into the magnet room itself. For example, if you're helping consent a patient or a volunteer, to actually get them into the room and onto the table. And then there's level 2, which is actually operating the scanner. Now the techs operate as level 2 always, so they have a completely different set of criteria that they have to go through. If you want to find out more about how to achieve these different levels, just go to the MR Center website, okay? And I'll refresh that later. So the basic magnet hardware, this is just a general diagram here that we're showing. So the parts that I want you to be most aware of are, first of all, the main magnetic field, which is these main superconducting coils here. This is the main magnet. We've got RF transmitters within that magnet, as well as receiver coils, gradient coils, and obviously the RF cabinet, or the actual room itself has certain pieces of metal, let's say, in the wall to dissipate some of the fields that are actually coming out of the magnet that we're not actually able to dissipate completely. And so each one of these, so the main magnet, the RF transmitter, and the gradient coils all have their own separate set of safety checks in place that we'll talk about today. So first of all, just to give you a sense of how strong this magnet is that we're using, so both our 3T and the one over at Children's are operating at 3 Tesla, which is 30,000 Gauss, which, just to give you a sense of scale, a junkyard magnet is usually about 1 to 1.5 Tesla. So these magnets are twice as strong as what you would need to pick up, let's say, a car, which is why you can see why those two 80-pound metal tines from a forklift could easily fly across the room. And obviously the Earth's magnetic field, which we're all in right now, is at a field strength of about 0.3 Gauss or about 30 microtesla. Okay? So how do we generate this giant magnetic field? Well, if you think back to your high school physics, it's basically just a solenoid or a loop of wire. You pass a current through it, and your old right-hand rule, fingers curl in the direction of the current, and your thumb points in the direction of the B0 field, okay? Now, we don't typically generate this magnetic field with copper, let's say. Well, the reason is because copper has a low resistance but not zero resistance, which means that first of all it dissipates heat, and it also means that we need a constant energy supply in order to keep that current flowing. Whereas if we use superconducting materials, they allow conductivity with absolutely no resistance, which means no heat, and also if we were trying to get a really high magnetic field with copper wires, it might actually melt. It might be impossible to actually get that magnetic field going. But when we get our superconducting coil up to field strength and down to 4 Kelvin, which is what liquid helium is at, then we get free conductivity of the current, which allows us to have a constant magnetic field. And just so you know, the recent incident at the Children's Hospital cost about $66,000 to re-ramp the magnet back to field strength. So obviously we're not turning this magnet off every day at the end of the day and then spending $66,000 to ramp it back up every morning. And so niobium is one of the typical materials combined either with tin or with titanium that we use to build these superconducting coils. So just so you know, the reason we use this B0 field is it causes all the protons, the hydrogen protons, the little magnetic fields in those hydrogen protons to basically align and precess about the direction of that magnetic field, causing a net bulk magnetization that points in the same direction as our B0, okay? And what we do with MR imaging and MR spectroscopy is we manipulate this M0, okay? And that's it for the physics lesson other than this slide. So one of the ways that we manipulate those magnetic fields is by applying oscillating fields that are rotating in the transverse plane. So the easiest way to think about how we generate this with our RF coils or our B1 coils is if you think about two pairs of coils, one going up and down, one going sideways, you basically bounce a magnetic field between the two of them. One acts as a sine wave, one acts as a cosine wave, so they're 90 degrees out of. And when you add those two things together, you get a circularly rotating magnetic field that is now perpendicular to our B0 field, okay? The reason that we call it a radio frequency coil, or radio frequency pulse, or RF pulse, is because at the magnetic field strengths that we typically deal with in our imaging, the frequency of that oscillation, or that omega 0 that I showed, falls within the radio band of the electromagnetic spectrum. Another type of coils that I briefly talked about is gradient coils. These basically just manipulate the experienced magnetic field of the spins as a function of position within that solenoid bore, okay? All right, and so for example, if we were to not have any gradient on at all, we assume that all of our protons in the Z direction are precessing at the same frequency. If we apply a positive gradient, it means that these protons are now precessing faster than these protons in the Z direction, okay? All right, so those are the main components of the MR suite that we've talked about. And so each one of those has a specific set of safety criteria that have to be met for safe operation. And we'll start with just the main magnetic field. So as I talked about, the superconducting magnet, it would be way too expensive to try to ramp it down and ramp it back up every day. So that magnetic field is always on. So the first rule of MR safety is the magnet is always on. Always be cognizant that that magnet is on 24 hours a day, 365 days a year. And this is my own personal rule number 2. Never assume that everyone understands rule number 1. Because if you're calling a crash code, for example, those people may not be trained with MR safety in mind and may come barging into that room with all of their metal projectiles, okay? So never assume that anybody coming into the suite has an understanding of rule number 1, okay? here are some examples of people ignoring rules 1 and 2. So you can see that this metal chair has flown into the magnet. This is a floor buffer. So here they've assumed that the cleaning staff that is coming in to buff the floors in the MR suite are trained and are using MR compatible floor buffers. I'm not even sure if those actually exist. Some more serious examples are hospital gurneys, ICU beds, often contain a lot of metal and will fly across the room and get stuck in or next to the magnet. Okay. Now, I talked about this briefly, but we don't just have a magnetic field inside the bore. We actually have this fringe field where the magnetic field actually tapers off somewhat quickly, but not instantly at the edge of the magnet. So we have these fringe fields, and you can see the lines that are drawn around the magnet here. The one that is highlighted here is the 5 Gauss line, or 0.5 millitesla. So this should be indicated on every MR system, and the reason is because inside this 5 Gauss line, the magnetic field strength is strong enough to cause problems with these different types of devices and materials. Okay. I've already shown some examples of projectiles, but basically when these items get brought within that 5 Gauss line, they become an uncontrolled projectile or missile. And basically they will fly. No matter what you try to do to stop them, they are going to fly towards the magnet, okay? And anything that is between them and their projected path is going to either get pinned, crushed, or split in two. Okay, so obviously metallic projectiles compromise the safety not only of the subject that you're trying to scan, but also the technologists or yourselves if you happen to be in the way of these projectiles as they take off. So for example, paper clips or bobby pins can exceed 65 kilometers an hour at a field strength of half of what we're talking about. Okay? And that only goes up when we start getting to higher and higher field strengths. And then obviously the more metal the object has, the more attractiveness it's going to have to that main magnetic field. Okay? So there are obviously a lot of pieces of equipment within the hospital setting that shouldn't go in. For example, the ICU bed that I just showed. Certain types of equipment is approved to be up to a certain magnetic field strength. So for example, an item that is approved to be used at, let's say, 1.5 Tesla is not automatically assumed to be safe at 3 Tesla. There are signs that indicate that on the doors, okay? So these are just some examples of possible projectiles. It's certainly not an exhaustive list, and these aren't necessarily the only people that might try to bring those items into the MR suite. So obviously scissors and hemostats have very sharp edges, and I'm sure some of you have seen the MR safety videos where that you can actually let a pair of scissors go and it will split right through a watermelon at the edge of the bore. Imagine that being someone's skull. Obviously you don't want to take these items into the magnet. Okay, stethoscopes, that's a big one because if you're doing a clinical scan and the physician wants to be there to monitor the patient, they obviously need to understand rule number 1, that the magnet is always on. Okay, any questions so far? All right, so again, highlighting the 5 Gauss line. So anyone with a cardiac pacemaker or insulin pump or some type of chemotherapy pump or magnetic neurostimulators can't go inside that 5 millitesla or 5 millitesla or 5 Gauss line. Okay. So in addition to making sure that we're screening all of our personnel to make sure that they understand they can't bring metallic objects into the magnet suite, we also go through this extensive screening form with each one of our subjects. And it basically just goes through and makes sure that they don't have any of these things like pacemakers, any sort of metallic implants or bullets or shrapnel, anything that will either cause them either discomfort or actually cause them to die if they go inside that 5 Gauss line. Okay, who has not gone through this MR screening form? Has everyone done that? Is that part of level 0, I believe? I think so. Okay, good. So everyone is familiar with this, and now you understand exactly why we need to have this screening form. Now, slightly less serious, but still could potentially be annoying, if you take your credit cards into the magnet, you could completely erase them. Obviously, that's not necessarily a safety issue, but it could be a royal pain in your behind. It's something to be mindful of. And obviously, some of these devices, even though they may malfunction, they could also fly into the magnet, like the camera at the back of the room there, especially the metallic tripod that it's sitting on. Okay. So ASTM has created a classification series around 2006 that describe whether an object is MR safe or not. So if something is MR safe, it means that it's completely non-magnetic, it's non-conducting, and can be taken into the magnet and inside that 5 Gauss line. Some of these MR conditional devices, as I said, are only approved up to a certain field strength or up to a certain distance towards the magnet. So for example, a coil that is approved at 1.5 Tesla will probably not be approved at 3T, and also it's calibrated for 1.5 Tesla, so there's really no reason that you would actually want to bring it into the 3 Tesla field, but it's just something to be mindful of. And these are just the symbols that appear on those devices that basically describe their safety. And then obviously there are things that are completely unsafe, things that contain metal, ferromagnetic metal, or magnetic fields or electrical conductivity. Okay? Any questions? So in addition to screening, obviously, every person that is coming into the magnet room and making sure they've had proper training, we also put up these bright and colorful pictures. So these are actually pictures from the Siemens Family MR Research Center doors. This one's on the outside, the entrance to the level 0 clearance area, and this is actually on the outside of the scanner door itself. And the idea is basically to make sure that anybody that crosses through those doors understands that anything on their person or anything that they are trying to bring into the room needs to meet the MR safe compatibility. So we've talked about the safety issues regarding at least the main magnetic field, and now we'll talk about the radio frequency fields. Remember, that's the circularly spinning magnetic field that's perpendicular to our main magnetic field. It's not actually the rotating magnetic field that's the problem, it's the corresponding electric field that we have to worry about when we talk about this particular magnetic field. And basically, electrons interact with an electric field, and that can cause those electrons to move a little bit quicker or move much faster, and that corresponds to heating. That is actually how tissue can become heated, is by manipulating the electron shells around the molecules in the body. And so our radio frequency energy is deposited as heat into the tissue. If somebody has a particular metallic implant that may have some ferromagnetic parts to it, which is all on our screening form, the tissue around those implants can actually get heated far more than what you would actually expect for normal RF deposition of energy into the tissue. There are also some non-thermal effects. There is no conclusive evidence to support that these are both long-term and significant in terms of biological effects, but it's just something to be mindful of. So the amount with which we are allowed to deposit that RF energy into the body is called the specific absorption rate. And basically, the governing bodies in the various countries, either Health Canada, the FDA, the governing bodies in Europe and Asia and Australia, have set specific targets where you are not allowed to exceed how much RF energy you're depositing to the tissue. So basically, you can't exceed a certain amount of RF energy. It is impossible to actually violate those rules. The vendors have specific criteria that they are not allowed to exceed those SAR levels before they're even allowed to sell you a magnet, let alone install it and allow you to start scanning subjects. But it's something that you may have included on your ethics forms or your consent forms that you have to actually explain to them. But the nice thing is that you are not actually in charge of monitoring SAR. The magnet actually does all of that for you. So in normal mode, we're allowed to deposit less than 2 watts per kilogram over 6 minutes, or 6 watts per kilograms over 10 seconds. And this is when we're talking about the whole body, and then obviously we're even more conservative when we're talking about the brain. Again, these levels are actually set into the hardware and software of the magnet, so you do not have to abide by, you don't have to worry that you're going to violate these SAR deposition levels. But it's something to be mindful of if you're not running, let's say, in normal mode. Let's say you have to run in a slightly more conservative mode because let's say they have a stent, a MR compatible stent, but a stent nonetheless. What might happen is that increases or decreases the amount of SAR that you're allowed to deposit into the tissue, and therefore you may have to increase your TR beyond what maybe your study design is hoping to achieve. But that is why the scanner will pop up with a little warning and say we have to increase the TR because of SAR. Okay, any questions? All right, so that's the safety with regards to the radio frequency fields, and now we'll talk about those gradient fields. So one of the advantages of having very, very strong gradients and very, very fast switching gradients is that we can scan faster. Why do we want to scan faster? Well, it's less table time for the subject, but when we start talking about brass taxes, it means that we can actually put more people in the scanner per day, which allows us to basically stay in operation longer. But it's important to note that the faster and faster our gradients get, the more likely it is that there may be some reversible but impact on the subject. So if you talk about the change in magnetic field as a function of time, or dB/dt, as the pulses get shorter and shorter, the threshold with which people become either uncomfortable or intolerable gets higher and higher. Okay? So the faster we scan, the more cognizant we have to be of these dB/dt limitations. It's also important to point out that the regulatory limit for these thresholds is well below what you would get for either cardiac or nerve discomfort. However, you may have seen, especially if you're running functional scans, you may actually get a warning from the scanner that says subject may experience peripheral nerve stimulation, and that's because of this fast switching. So it's just something to be mindful of. Okay, any questions? Oh, and it's also, so not only is the regulatory limit well below what the cardiac and nerve stimulation is, we're here in the optimal operating range. Okay, in addition to having these fast dB/dt switching gradients, the gradients also produce quite a bit of noise. And so we typically give them earplugs. This slide was recycled from, this is actually the sign on the Seaman Family MR Research Center 3T door, right next to the big giant one that says don't bring in oxygen tanks and wheelchairs. At least stood outside the door, let alone be actually inside the magnet when it's scanning. It's very loud. So make sure that you give them earplugs to reduce any possible hearing damage that may occur. Important to point out too, especially if you have if one of the technologists is in the room, let's say working with the gadolinium pump, let's say, they'll have earplugs in to protect them as well. Okay? So we're obviously operating at above freeway traffic here for some of these sequences that we're running. Okay, so just to review some of the guidelines for safe practice. So because the magnet is on all the time, we have to be MR vigilant all the time. So 24 hours a day, 365 days a year, we have to be cognizant of the fact that that giant magnetic field is always on. Anybody that is going into that environment across that 5 Gauss line has to be properly trained, and that's where we talk about level 0, level 1, level 2 training. Whoever is actually operating the scanner is responsible for the safety of everyone involved, whether that be the subject, whether that be any research assistants that are helping you with some of these more complicated studies. You are responsible. So if you're the level 2 operator for that examination, you're responsible for making sure that everybody is aware and safe. So one of the obvious ways in which we can keep things safe is by having a controlled access area. And that's where we come back to this level 0, level 1, level 2. So you shouldn't be able to get through that door until you are at level 0. Okay? And then once you have level 1, you can go into the magnet room, and then level 2, you can be the operator of the magnet and the person in charge. Okay? So because the magnet is always at field, the safety procedures have to be in place all the time. And the reason that we want to do this is we want to prevent accidents. Remember, I said that MR is a safe imaging modality as long as we abide by all of the safety rules. Okay? So when you're, excuse me, when you're actually operating the scanner, there are also some things to be mindful of. For example, if you open the magnet door and you don't hear the cold head pumping, the ka-chunk, 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 then you need to inform somebody and try to get the pump turned back on. That pump controls the liquid helium and the liquid nitrogen that keep our magnet at field. If you experience any louder than normal noises, so for example, some sort of grinding noise in addition to that cold head ka-chunk, ka-chunk, you need to inform someone. Obviously, if you see sparks or can feel particular, let's say a head coil starts to heat up, you need to inform someone, inform the technologist, inform, I believe, Louis, and possibly GE as well. And obviously, if you smell smoke or any weird flux smells or anything like that, you need to be reporting that. And report any unusual events, okay? Obviously, don't operate any open equipment because the little electrical components in that may be MR safe, but they can still heat up and burn someone. So just to summarize, everyone that comes within that 5 Gauss line needs to be properly trained and or screened if you're talking about your participants. Patients should be monitored for some of those irreversible effects like the peripheral nerve stimulation. Operators must be familiar with the operation of the actual scanner, know when to press the emergency stop button, know when it's appropriate to press the quench button. You learn all about that in your level 1 and level 2 training. And safety is an ongoing process. Because the magnet is on all the time, we have to be mindful of our safety procedures at all times, and we may have to make modifications to that the protocols that we have put in place. So just to summarize some of the safety issues that we talked about. So the main magnetic fields, the way that we deal with them safely is by proper screening of people that are operating the magnet or coming in contact with the magnet or the people that we're actually scanning. The radio frequency fields and the peripheral or the nerve stimulation, those are standards that are put in place that are somewhat out of your control, but just be mindful of them. And obviously we talked about scanner noise and how it is recommended that you give them earplugs before they go into the magnet, okay? And so again, if you want additional information on level 0, 1, and 2 training, please go to the MR Center website. I think it's in this restricted content thing here. Make sure if you haven't already done so, please sign in. And that concludes my section of the talk.